Today, first, I'm going to give another model of the transfer line that we talked about yesterday and, and do it in a component-like way, just as we did for the simple server from yesterday. And then I'm going to talk a little bit about event priorities, because even though for most of what we do here, that's not going to be so much of an issue, but it's something that eventually comes up. And so it was something I actually showed a little bit when I was showing I think there was the for loop a couple days ago. And then just a little snippet about modeling an if condition. Again, strictly speaking, the state transitions in event graph methodology in its purest form, strictly speaking, there's no if statement. Part of the reason for that was that the guy who came up with these was interested in something really as minimal as possible. And so, an if condition is something which, as a programmer, we're used to having. But as a state transition, what it tends to do is it tends to hide the logic. And so rather than hiding the logic by allowing an if in pure event graphs, what they do is they have them represented as certain events. And I'll show you what that's about. And actually, given everything that we've covered so far, you should be able to figure that out for yourself. However, the understanding and being able to design models using these event graphs is a bit of an acquired skill, which is why I'm going to be having you do various modeling exercises, both in the assignments as well as the ones that I demonstrate here. Okay, so let's red. All right, so the transfer line component. Remember, the idea of the transfer line was taking the tandem queue that we'd done before and just expanding it out to an arbitrary number of sequential processes. So the idea is that a part starts at the first workstation, goes to the second and the third and the fourth, however many they are, and then finally when it reaches the last one, it leaves. So if you remember, what we did yesterday is we looked at the multiple server queue, and we recognized that this arrival pattern of the self-scheduling edge with a delay is something which appears a lot. And secondly, it was something that in a way is kind of exogenous to the system. In other words, it's some type of process that injects these arrival events into the queuing system, where the servers are. But in a sense, those are kind of separate. It's exogenous to it. And so with the simple server component, remember, we split up, we said, well, we have this arrival process thing. Let's just sort of stick with that and then only do the pieces associated with the server. And now we're going to do that for the transfer line. In other words, we're going to model only the part of the system that actually processes the parts. Now, we're not going to model the arrival of parts, but then what that does is that opens up something which is important to understand how the sim event listening stuff works. Okay, so parameters, they're exactly the same as before. We have a certain number of workstations, and the advantage of having that as a parameter means that the same model will work for any number of workstations. So for any facility that has this same structure, we can use this very same model for representing that. All we need to do is specify how many workstations there are, specify what the service times at each workstation is, and specify the number of servers at each of the workstations. And again, just as with the simple server component, we don't need the arrival times, since the part arrivals are going to be done by a separate component. And well, we have that separate component being the arrival process, but then as we will see, the arrival process by itself is not quite sufficient. So we're going to need to tweak that a bit. And I'll in terms of it, well, we'll show you what the tweak is, both in terms of the design as well as the, I'll show you the code on that as well. So if you haven't pulled my class code, that's something that would be useful to do, because I put some new stuff in there yesterday. Okay, now the state variables, just as with the simple server and the multiple server queue, notice that what we've been doing all along is just doing counts. I use the term arrival of parts, but that's just from a conceptual standpoint. We aren't modeling the individual parts, the individual customers. We're only counting them in this model. There's a very good reason for that. One is that's all we need for the kinds of measures that we're interested in at this point. The second is that when you only have these counts, the model is blazingly fast. All we're doing is the only work that the computer is doing is, well, the event list processing. That's something it's going to have to do anyway. But the state transitions are just integer arithmetic, which is one of the fastest things that you can do on a computer. So these models are extremely fast. Now, what we pay for it is that we're not able, at least out of the box, or we're not able to directly estimate some of the measures we might be interested in, such as for example, if we're interested in the average time in the queue, that's not something we can directly calculate. If we're interested in the average time that it takes to go through the workstation, again, that's not something that we can directly calculate here. And, you know, things like in this case, another measure we might be interested in, what's the average time that a part takes to go all the way through the workstation. Again, that's not something we can directly calculate. However, if we confine ourselves to the averages, we have that Little's formula, which is something which absolutely holds. It holds when the system is empty, and it holds approximately when the system goes for a reasonable amount of time. Again, under all very mild conditions. Okay, so our state variables again are just similar to the multiple server queue component, except that it's an array now. So we have an array of integers, Q, which represents the number in the queue at each workstation. So Qi is the number in the queue at workstation I. And I goes from 0 to n minus 1. And each one is going to be initially 0. And likewise, at each workstation, we're going to have a number of available servers that to begin with is going to be k sub I, that is the total number of servers at that particular workstation. So again, the parameter k is going to be an array. The state variable s, the number of available servers, is also going to be an array. Okay, so and this is the parameters and the state variables are both identical to what we did yesterday, with the exception of not having the T sub A. That's the one exception. Okay, and it looks like this. And one of the things that you should, I'll go through this in detail, but one of the things you should at least note off the top of your head is that this looks a lot less cluttered than the full model. See, because the full model had all kinds of other stuff in it. This one is much cleaner, a little bit easier to pick out exactly what the structure is. Okay, and there are two pieces to it. This pattern And this pattern is, oops, and this was kind of hidden by this, but this should be, here, I will correct it on the slides and upload a, I think that got hidden behind here, either that or it was left off. Anyway, this for loop, event graph for loop concept is something which, when we have state variables that are arrays, this is the standard way to initialize it. Okay, so what does this do? Run now. Now, normally we would initialize all of our scalar, all of our state variables here, all scalar variables. If there were scalar variables, we would certainly initialize them here. In this case, we don't have any scalar variables, so we're just going to leave that blank. The array state variables, we're going to initialize them one at a time using this for loop here. Okay, so run will schedule init 0. Init 0 will set S0 equal to K0 and Q0 equal to 0. Then let's say, supposing n equal, let's make it 3 just to, so if n is equal to 3, then 0 is less than 2. Is 0 less than 2? Yes. So then it will schedule another init with 1. And then init 1 will set S1 equal to K1 and Q1 equal to 0. Then is 1 less than 3 minus 1, 2? Yes. It will schedule init 2. So init 2 is, it will set S2 equal to K2 and Q2 equal to 0. And then is 2 less than 2? No. And so it'll stop there. So this piece down here will simply initialize the state variables. Now the main component, the main logic is, of course, is up here. So, and this should look very, very familiar. So when we have an arrival I, and again, it's important to understand now, the I here is an argument on the event, just like an argument on a method. So when we have an arrival I, what that means is an arrival to workstation I. And when there's an arrival to workstation I, it increments the number in the queue at station I. Then what does it schedule? It has one scheduling edge. What the condition is SI bigger than 0. In other words, is there an available server at station I? And if there is, it will schedule a start service passing the value I. So in other words, an arrival at station I may schedule a start service at station I, but not any other station. Looking at the start service at station I, what it does is it decrements QI and SI. In other words, it takes a guy out of the ith queue, it takes a server out of the ith workstation, and then schedules an end service with a delay of the service time at station I. It's very small, but there's a subscript there. That's T, that is T sub S sub I. And that's important because the service times at each workstation are going to typically be different. And so when we have a start service at station I and say, well, when will this finish? It has to be from the service times at that station. Oops, okay, so yeah, my internet was going flaky there for a little bit. My apologies. Okay, so it schedules an end service at station I. Say again, where did the I come from? It was passed. And finally, when an end service at station I occurs, it will add an available server at station I. And then it has two things to look at. One, see, because every event schedules every scheduling edge coming out of it is what gets processed. And only the ones, of course, if there's a condition, it's only the condition that blocks it. Okay, so if there's when the end service at station I occurs, if there's still somebody in the queue at station I, then it will schedule another start service, again, passing I. So it schedules a start service at station I, no other station. But there's one more thing. If this is not the last workstation, then it will schedule an arrival at the next workstation. And what's the next workstation? That's I, if I'm at station I, and what's the next one? It's station I+1. So this will schedule an arrival at station I+1, and the whole thing keeps going on again. And what's the one time we don't do that? The one time we don't do that is if we're at the last station. At the last station, there is no next station, and so we just don't do anything. How do we know when we're at the last station? Well, if our station is equal to n-1, because n-1 is the last station. So the edge condition on this scheduling edge from end service to arrival is that I is less than n-1. Okay, so that's any questions about this, about what we're doing here? Is this fairly straightforward? Okay, makes sense. All right, now we have a little bit of a problem, because if you remember, we used the arrival process to trigger arrival events for the simple component. But now we need arrival events that have an argument I. And the way that the event matching works, if I'm a component and I hear an event, when I match it, I have to match it exactly, meaning I have to match the name of the event and its argument. If there's a mismatch in either one, then it doesn't take place. So that's our problem. The arrival process can't work to drive this component because the arrival process schedules arrival events with no argument. But the transfer line component needs an arrival event with an I, with an argument I, which is going to be an integer. Okay, so the arrival process by itself does not work. So what can we do? Well, what we can do is we can, first of all, envision something I'll call sort of a creator arrival process. So conceptually, it looks something like this. So here we have the arrival piece. In other words, this pattern is something which produces a stream of arrival events delayed by a sequence of inter-arrival times that we specify, usually with a random variable. And then every time an arrival event occurs, it will schedule an arrival I, but passing it 0. And what that will do is that will basically trigger an arrival event in the transfer line component with an argument of 0. That's the first workstation. So in other words, is it clear that this guy will produce a sequence of these arrival events with the correct argument? And this event will be heard correctly by this. Actually the arrival event will also be heard, but it'll be ignored. See, because when this component hears an arrival event, let me take away, let's just sort of take away some of this clutter here. Okay, so when I hear an arrival event, then the way it gets processed says, do I have an arrival event with no argument? And the answer is no. And in that case, you just kind of ignore it. When I hear an arrival event with an argument of 0, I say, I have one of those. I have an arrival event that has an argument, and the value of the argument is 0, so I will schedule an arrival event with 0 on it. And once that happens, then that kicks off this whole sequence of other events, which eventually will lead to the end service of it. Okay, so that's what this will do. Now, there are two ways to build one of these things. There is I could just build it from scratch, just like this. I mean, this is very straightforward. A very, as you may or may not guess, what I found is that having lots of these little small components are very useful. Small is good. Okay, and this is small, but I'm lazy too. So the lazy way is to say, well, look, I already have an arrival process. I've already done that. Okay, so we've done this conceptually. I've made you implement it, and of course I've implemented it as well. And so I can subclass this, and in event graphs we can kind of conceptually do that as well. And this is what it looks like. In other words, I've already implemented this. I already have this in hand. And now I'm going to add this little piece to it. So I'm going to subclass it. And you all should understand conceptually what the subclass is. And so the idea here is that this arrival event, which is going to also invoke this arrival event in the superclass, is simply going to schedule an arrival event passing at 0. That's all that it does. And I say this is the lazy way, keeping in mind that at least in certain contexts, laziness is a virtue of programming. In other words, my laziness is I don't want to write all this stuff again. I've already written this. I've tested it. It works fine. I don't want, I've already written this code. I don't want to write it again. So I'm lazy in that I only want to write this one little piece, and then I get a good bang for my buck, because with only a very small amount of code, I get more functionality. Okay, so what I'm going to do now, I'm going to pause here and show you what that looks like. Tell you what, I am going to try to make this a little bigger here. Editor. Oops, fonts and colors. Let's make this. Okay, so is that a little easier to see? I hope. All right. Okay, so here I'm calling it the arrival process creator. And again, this is in the code that I've pushed. So if you do a pull on the on my code, then you will see it. Okay, so here we all know what subclassing is from the Java class. So but now instead of extending SymEntityBase, which is the base class for everything we're doing, I'm going to extend arrival process itself. Okay, so now I always want a 0 per argument constructor, so I need to write that. And then I also, because I have parameters, I also want a main constructor, which has the parameters as arguments. So typically, again, for all of the component implementations, we will have that. We will have a 0 argument constructor for purposes that we may or may not get to at some point. And we have a sort of a main or master constructor, which has all of the parameters, all of the simulation parameters that we have, not the state variables, only the simulation parameters. So in this particular case, the setter is already in the superclass. So if we go here, so the arrival process constructor already is setting this. So all I need to do is just call super, and I'm in. Okay, so let's look at what the actual key thing is. Okay, so I have an arrival event, and remember, events in the event graph translate into a method with the little words, the magic words do before it. So do arrival corresponds to the event arrival. And since I want the superclass arrival process is what creates the sequence of arrival events, I want to make sure that happens. I don't always want to invoke the superclass event. In this case, I do, because if I don't, then the arrivals just aren't going to be showing up. So that will keep the arrival events coming. And then here I'm scheduling the arrival event with an argument of 0. So let's look at how that works. Okay, for this form of wait delay, the first argument is the name of the event. Okay, arrival, that matches this. The second is the delay. In this case, the delay is 0. In event graphs, when you leave the delay off the scheduling edge, it's just assumed to be 0. In a programming language, that doesn't work. We have to be explicit about it. But then the final argument is, in this case, an integer, which is 0. So then when that happens, the do arrival event with the integer argument is going to get executed. Now, notice that there's nothing in here, no state transition, because no state transition was specified in the event graph. And that's okay. In this case, the only purpose of this event is to be heard by something else, in this case, the transfer line component. But any component that has an event called arrival with an integer that would accept a 0 as a legitimate argument can be used for this. Okay, and that's all there is to it. So in this entire class, almost all of the code isn't really code, it's just kind of wrapper stuff. So we have constructors. I have this empty event, and then I basically have two executable lines of code. So that's not very much, but I get a big bang for the buck, because now all of a sudden I get all of the stuff that the arrival process had together with the scheduling the new stuff. Okay, so here's how we do that. Now in this case, I'm going to be using the beta distribution. That's something we haven't seen before, but you should all be familiar with or at least have heard of the beta distribution in your probability class. At some point, they must have at least mentioned it. It's a probability distribution, just like similar to the gamma, right? And we're gonna kind of watch the state transitions. Again, there are no states for here, but our superclass, the arrival process, is going to be counting the arrivals. And just in part to make sure that that's happening correctly, we want to do that. So we're going to run in verbose mode. And then this is a second way to stop the simulation. Up until now, we've always said, oh, stop at this time. But if you remember in the first written assignment I gave you, I said, stop after the 4th end service event. Okay, so that's something which can be implemented in SimKit as well. And so I just tell schedule to stop. The call is stop on event. And what I do is I give it this is how many events, this is the name of the event, and then this is the signature of the event. Now, the one little catch is that even if the signature in this case is an int primitive, when we're specifying in this way, we always have to give the object wrapper, and that's because under the hood, it's actually auto boxing it. It's automatically kind of promoting the int to an integer object for a variety of reasons. Okay, so what this says is stop after the 5th arrival event that has an integer argument. Again, running it, we just do a reset and a start simulation. And let's look at what that looks like. Okay, that is kind of tiny. Let's see if I can make it bigger. Oops. Can I make it bigger? No, I can't. Where the heck would you go? Can I? No. Not sure. Anyway, okay, so it'll just have to be a little tiny. All right. So here we go. So here's the run event from, where's the run event from? Because we didn't define one. We didn't define one here, but because we extended the arrival process, the run event is definitely there, and as is the reset. So remember from the Java class, when we subclass, we get everything in the superclass, everything. Okay, so number arrival 0, the current event is run. We schedule the first arrival. That's from the superclass arrival process. Okay, so now our arrival occurs. Our number of arrivals increases to 1. We schedule the next arrival there, but here's our arrival with an argument of 0. And so what we see from this is that when we schedule an event that has an argument, the argument is listed on the event list like this, in curly braces. Why curly braces? Who cares? Okay, so now here's this arrival event with the argument of 0 occurring. Okay, now it's not doing anything right now. If we hook this up to the transfer line, if we had it, then something would happen. It would trigger some more events. Okay, so here's another arrival. Again, here's another arrival with an integer 0. And then here's it occurring. Here's the second one. Remember, these little square brackets are counting the number of times that that particular event occurs. And then notice that the count is separate for, so even though we have arrival 0 and arrival with no arguments, those are separate distinct events. So in other words, an event is specified by its name and its argument. And if it has no argument, then that's different than an event with an argument. So the arrival event with no arguments is a different event than the arrival event with an argument. And that's identified here. So notice that here, this is the third arrival with no argument here, and this is the third arrival with an argument. And there's the fourth one with an argument, the fifth one without an argument, and then the fifth one with an argument. And then that's it. What happened? Well, because we specified that we should stop after the fifth arrival event with an integer argument, it stopped here. Now, what if we wanted to stop after the fifth arrival event with no arguments? Well, then we would say stop on event 5 arrival, but no integer there. And if we run that, we see that it stops after the fifth arrival event with no arguments. Okay, so this is how see the comment. Okay, let's see. Getting the message. Okay, well, if you're trying to run it from the green arrow, then it doesn't have a main class set, and you just choose the main class. So if I were to run that, I simply select, okay, now you can't see that, can you? All right. All right, so that's what that is. I'll deal with any glitches afterwards. And let's go back to our PowerPoint here. Okay, so that's implementing what was going on here. And the code was simply this here, right here. That's all that was. Okay, so now if we wanted to hook this up to the transfer line component, this is how we would do it. We would have this creator arrival process, and then the transfer line component would simply be listening to it. That's what this indicates. And again, when that happens, these arrival events with 0 argument would then trigger the arrival event in the transfer line component. Okay, well, we're not going to do that within the code here, but I've showed you how to subclass. And this is actually the second example of subclassing, and also kind of how to, the other new thing was how to stop after a certain number of events. You have to be a little careful of that, because if you fat finger anything in there, then it'll just kind of run wild and you'll have to stop it by other means. Okay, and that brings us to priorities. Now, normally, if you notice that all of the probability distributions we've been dealing with have been continuous probability distributions. We have exponentials, uniforms, gammas, and betas. These are all continuous random variables. And you may or may not remember from your probability class that when we have continuous random variables, the probability that 2 of them are exactly equal is literally 0. Again, if you don't remember this, well, I'll say it, and so you'll know it. If I have 2 random variables that are continuous, again, like normal or exponential or gammas, the probability that 2 of them are exactly equal is 0. That's part of what makes them a continuous random variable. So typically, the only time that we have events occurring at the same time are going to be in the initialization, like in that for loop, or just in general when events are scheduled with a 0 delay. That is, one event occurs, then the next one. However, sometimes it happens that we may have just by chance a collision. In other words, 2 events may be scheduled to happen at exactly the same time. Now, both event graph methodology as well as the SimKit implementation are arbitrary when it comes to events that occur simultaneously. In other words, by default, you cannot specify without additional work whether one event should happen first or the other happen first. Sometimes you need to do that, and that's where event priorities come in. So again, and this is actually kind of the final piece of the methodology. If there's like a little circle on the event scheduling edge, in the case of an exact time tie with another event, the one with the higher priority occurs first. So, and that's just a way of specifying, just making sure that certain events happen before others.
Any question on that? If he didn't have the priority, if 2 of them hit at the same time, would it cause an error and stop, or would just the one that got there first, the one that was scheduled first?
Yeah, no, it's arbitrary. There is no got there first. In other words, if I have 2 events that are scheduled at this, well, if no priority is explicitly given, they have the default. There's a default priority, And if I have two events that that occur exactly the same time with exactly the same priority, then it is unspecified which one happens first. In other words, your model should not depend on that in order to work properly. That is, if I have a situation where two events could happen simultaneously, then my model should be written in such a way that which order they occur have no impact on how the model behaves. However, in the case of, and again, this is something which typically does not come up with continuous random variables. But every now and then you might be in a situation where you're using discrete random variables. Actually, there's a simulation I've been working with the Naval Support System where, for a variety of reasons, they have their time, they want to do everything on a day-by-day basis. So within the day, I need to specify priorities in which things happen. Things like the demand for a part will come in, and a part may get ordered. And so in that case, I need to specify that the demand happens first and the order happens second. Why? Because I want the order to take into account any changes in the inventory level that the demand of that day has caused. So for our multiple server queue, or our simple server component, the key here is that we need to have this start service event happen before any of the other events. In other words, we want to give it a high priority. And this is how we do it. And again, this in all the years that I've been using this model, there has never once been a collision. However, if discrete random variables are being used for the service times and the inter-arrival times, then there is the possibility of a collision. And in that case, we want to make sure that the start service event happens first before either arrival or end service events. And we specify that by putting this high priority on. And the way that it works internally is the first criterion is the scheduled time. And if you think back to the Java class when we were doing our comparators, the comparator for event objects is the first criterion is the scheduled time. So every event, if I have a pile of events on the event list, the one with the smallest scheduled time is the one that's going to happen next. What this says is that if for some reason I have an arrival event that's scheduled at exactly the same time as the start service event, then the start service event should happen first. Okay, that's and we'll in the basically in the computer assignment, I believe I have you do that again, and it's just really a stopgap measure in this particular case, because there's no control over whether somebody who uses this component decides to use a discrete distribution or not. Again, discrete distributions are typically discouraged for this because usually we have, continuous distributions tend to work better, but every now and then there's the other thing. Okay, so that's and the thing to remember is that this priority only applies as a tiebreaker for events that are scheduled at exactly the same time. Okay, and then the final few things is that supposing, okay, this pseudo code should look very familiar to anybody who's done a lick of programming. It's basically an if-else statement. So if condition I, if this is true, then I execute B, else C. And as I said, in pure event graph methodology, we don't have, I can't put this, well, I mean, I can, but you may not. In other words, you can put this in as a state transition, but you may not. In an event graph, it's incorrect. In an event graph, this is not allowed. However, if I want to represent that logic, this is how I do it. So here's an event A which is where the if statement would be taking place. And remember, there's a Boolean condition on the scheduling edges. So I is the Boolean condition. And if that's true, then this would execute event, in this case, event B. And if not I, then it executes C. So this event graph snippet has exactly the same logic as this programming snippet. So this is how we model an if. Now, what about an else if? So let's say if I wanted to model to something like if I, then B, else if I, C. So here's how I would do that. I would actually create another event D. So here's if I, then B. Okay, we have that. That should be straightforward. The else, now we're going to have the not I, and that's going to schedule a D here. And then it in turn, here's the if double I, and there it is, just scheduling C. That's the verbose way to do it. Or I could here's an alternate way, is I could simply schedule a C and have as my condition not I and double I. Okay, so instead of this, I could just do them both like this. And maybe that actually would be slightly preferable. Okay, but either way, it gets the job done. Now, supposing I'm in a situation where I have, just sort of some complex logic, and I want to execute one or more of 3 events. Okay, so now I have 3 Boolean conditions here. And any one that's true, so when event A occurs, every one of these that's true will schedule the corresponding event. So let's say if I is true and double I is false, but triple I is true, then events B and D will be scheduled. On the other hand, if none of them are true, then nothing gets scheduled. Or if only I is true and II and III are false, then only B gets scheduled. So this is how we can control in a very, by combining all of these, you have a very rich set of capabilities for logic that we can do.